Today I'd like to introduce our new high-speed scan head, the Polytech. All right, the question is, why would you use a polygonal scanner rather than a Galvo XY scan head? Polygons historically have been used for example, your home laser printer. That's one application where you're trying to cover an entire field rather than just spots within a field. Inspection is a great application for polygonal scanners. We do systems that are retinal scanners. We also get involved with agricultural sorting and inspection, where you're trying to scan every pixel. If you're using a Galvo XY head, they're much faster in a lot of applications where you're just going to certain locations. But if you're trying to cover every point in the field, that's where polygons shine. Now, just recently, there's really been no reason for polygons to be used with pulse lasers. The reason for that is that the rep rates haven't been high enough. If the rep rates are low, there's no galvanometers work just fine. As you start getting above about 250 kHz, all of a sudden the galvanometers can't separate the pulses well enough to get the most out of your laser device. So with a lot of lasers now coming online that are 250 kHz and some pushing into the low megahertz range, you start looking at a polygon to be able to get the most out of your laser. Now we offer two different lines of scan heads, the Polytech, which we're featuring at this show, and the Hyperscan. The Hyperscan is a true XY Galvo scan head. It's got two galvanometers for compensation as well as a high-speed polygon within it. The Polytech is more of a line scanner with a galvanometer in the cross-scan axis for compensation. Now, I'm not sure how familiar you are with vector versus raster scanning. Vector scanning, you move the point from point to point. It's a continuous line. It can dwell on spots, and it only covers the area that you need to make marks. Whereas raster scanning, it has to cover the entire field, and it's done much in the old way of a cathode ray tube. We're scanning line by line to cover the field. A lot of applications for raster scanning that we're seeing are inscribing, ablating, inspection, and printing applications. Some of the obstacles to adopting polygonal scanners, their customers have been used to complete solutions. Historically, polygonal scanners have been sold as standalone component devices and not offered up as a complete end-to-end customer solution. We've been designing application-specific scan heads for 30 years for a nice variety of applications. What we're trying to do now with this Polytech unit is make a standard semi-custom unit for a variety of applications. Polygon scan system also requires some knowledge of optical design to get the most out of the system. You have to worry about start of scan components. You also have to worry about polygon-induced errors, such as banding, jitter, bow, and scatter, and how to compensate for them. The Polytech is the answer to what the market's been asking for, a plug-and-play solution. It's a high-speed line scanner, similar mounting to conventional galvanometer scan heads. It's a configurable design. It's designed to work with anywhere from a 10 to a 14 faceted polygon. It's designed, we've got three different models for 355, 532, and 1064 nanometers, and coming out with a CO2 over the summer. And we've teamed with Jonas Gerko and Landmark Technologies to create a custom version of WinLay 6 that operates as the marking software behind this. Typical applications that we're finding customers asking about it are for inline laser printing, also flexible PCBs, ablations for layer interconnects, and for broad area surface texturing. What's inside the polygon, it's a fairly simple optical device. It's got a very accurate start of line sensor system to give you a very good registration at the start of the scan line, where all the timing comes from. The input aperture is 15 millimeters. It's got a scan speed up to 800 lines per second, and pixel placement accuracy on the order of plus or minus 5 microns. Scan lengths are about 80 millimeters with 150 millimeter focal length scan lens, of course scan lens dependent. And this is just a GUI screenshot of the Polytech control software. Again, it's Landmark's WinLay 6, so if anybody's familiar with that, it's just a customized version of it to run a polygon in raster mode. In order to get the most out of a polygon scan head, you need to have the high performance components inside of it. The heart of the system is a high performance polygonal scanner. We've got a lot of years of refinement into this device. The scanner incorporates a diamond machine mirror, brushless DC motor and ball bearing spindle. We're a very vertically integrated company, and all of this stuff is made in-house. We wind our own motors, we diamond machine our own mirrors, and we manufacture our own spindles. The polygon mirrors, raw aluminum comes in one end of the factory, and out comes finished mirrors on the back end, including the thin film coating on the mirrors themselves. We design either gold or aluminum base with a multi-layer dielectric stack. The motors, we make both AC hysteresis synchronous as well as the more common brushless DC motors. We've got our own winding machines, so we can custom tailor the windings to the application. The type of spindles that we have are ball bearing, aerostatic, and aerodynamic. Currently in this model we use a ball bearing spindle, but we have the ability to put in aerostatic or self-generating air bearings as well. Okay, in the galvanometer, we've been acquired by Cambridge Technologies, so we have now access to the best galvanometers out there as well. The 6230H is the galvanometer that's inside this device. It uses their SCA 671 servo, and their 15 millimeter aperture mirrors coded for, in this case, 355 nanometers. System design configuration considerations, things you have to worry about when you're designing a system like this. Star-to-scan subsystem with the appropriate filtering. We've got a very low level of star-to-scan laser in there, so you have to worry about the issues involved with very high power lasers and the effect it might have on the star-to-scan subsystem. Good filtering with no fluorescence you have to worry about. Also laser high frequency clocks. You have to look at the laser you're using and ensure that it's got a higher frequency clock than the frequency you're operating at. In the CW world, you don't have to worry about this. You just use an acousto-optic modulator, turn on the beam when you want it on and when you want it off. But with pulse lasers, you have to find one that's got either a sync circuit or it's got some sort of pulse EQ mode where it can actually time like an 80 megahertz higher frequency clock and do pulse picking based off of that. That way you can get good registration of the dots from line to line. You have to worry about your polygon line-to-line repeatability in scan as well as cross-scan. In scan, you have to worry about the polygon jitter. In the Galvo world, inertia, you hate it. But in the polygon world, inertia is a good thing. It stabilizes the scan system. Cross-scan wobble you have to be concerned about. We manufacture the scanner to about 6 arc seconds of wobble, just so you don't need a passive cross-scan correction system. You have to watch the coatings that you use, especially as you're moving into the pico and femtosecond world, as far as coatings that can withstand the high energy pulses. Now, one of the first applications we've run across for this device, we built in our apps lab we're using a coherent Avia NX laser, 355 nanometer wavelength, pulse width of about 30 nanoseconds. Its rep rate was about 250 kHz, and we use a very accurate Aerotech translation stage for the second axis. We're marking in the UV plastic material. The reason why we chose 355 for this application is the customer didn't want any burn marks that you would typically get in the near infrared. It was burn marks in plastic materials for medical applications end up being sort of bacteria growth centers. So you rather use a cold marking process like a UV laser. That way you end up with actually treating the material underneath the surface and it's smooth on the surface. Just the applications lab, the Polytech device is buried inside here. The coherent laser is up top, bringing the beam down into the device, and the target is on the translation stage underneath. We've had several different varieties of lasers from 355 up through about 1064 nanometers on this, doing different outboard. The results, we can put down 300 dpi very quickly, much faster than can with inkjets. And there's just a close-up of the pixel placement accuracy that we're achieving with this. Good registration, because the laser actually has that good registration. It's got an 80 megahertz internal clock that the pixels are synced up to. So even though we're only writing at 250 kHz pulses coming out, it registers to 80 megahertz. So definitely sub-pixel. And the laser requirements, number one, of course, you need a pulse-on-demand laser, so you can pulse pick. And second, it works the best with synchronization circuits. There's a variety of lasers out there now that are coming online that have this type of synchronization that allow us to register the start of scan. The reason why you need that is the polygon wants to be the master clock, and the laser wants to be the master clock. So you have two master clocks fighting each other. So you need to find a way to get them synchronized. Now, just have a short video.
Please call or email Lincoln Laser for more information or to arrange a demonstration.